Thermal analysis. Investigation into the suitability of housing a DAGU board in a robot chassis. This is a presentation from Group 9 for the Heat Transfer Assignment 2. Introduction. Over the past 2 decades, the usage and need for robotics in various human activities has increased enormously. In hazardous environments like nuclear accident sites, robots play a vital role, performing tasks that are too dangerous for humans. Due to the harsh environmental conditions, it is important to ensure that the microcontroller and related circuitry is housed safely. The mechatronics robot design addresses this challenge by integrating the DAGU board within the robot chassis. But this introduces a new concern, which is the potential overheating of the DAGU board within the robot chassis due to limited ventilation. Since the chassis housing is not well suited for ventilation, mainly due to its lack of inlet and outlets for air, as well as a lack of space, the issue of cooling of the DAGU board may arise. This poses the question, can the DAGU board maintain its safe operating temperatures when situated within the robot chassis? To understand if the DAGU board could exceed its safe operating temperature, we are turning to CFD, Computational Fluid Dynamics Simulation. By virtually testing the board's thermal behavior within the chassis, we aim to determine any potential heating issues and explore solutions. This investigation is vital in ensuring the robot's reliability and safety in high-risk environments, especially in hazardous environments where its deployment is most critical. This investigation will offer a better understanding into the thermal behavior of mechatronic systems. Addressing this requires a combination of mechanical design, material science, and thermal analysis. It demonstrates the intersection of various engineering disciplines in solving real-world problems. This study aims to also enhance the performance and lifespan of the robot, ultimately contributing to the advancement of robotics in hazardous applications. This may lead to innovative solutions in housing electronic components such as the microcontroller and thermal management for robots deployed in various extreme conditions.
Hi, my name is Letutulas Kakane, the person who was responsible for doing the CAD for the DAGU board and the robot itself. So if you can see, this is the real-life representation of the DAGU board with all of its pins, and this is the microchip that we're trying to simulate temperature conditions around it. So what we did is that for our CAD is that we made the simplification that we did not need all these pins that were not inhibiting airflow to the microchip. We just only included the pins that were inhibiting airflow to the microchip, of which are these ones, these ones, these ones, these ones. So if you look at the left-hand side, this is the CAD representation of the DAGU board, and you can see that these are the pins that we've only included in the CAD because they are inhibiting airflow to the microchip. So the microchip is this red object here. And if you look here, this is the real-life representation of the robot. This is the front view, this is the back view, and this is the side view. So if you can see on the front view, you've got a distance sensor, you've got a manipulator, you've got a color sensor, you've got holes on the top of the chassis, you've got holes on the front of the chassis. And if you look at the back view, you've got a battery, you've got holes in the back of the chassis. However, our problem stated that we needed to have the DAGU board inside the chassis. So what we did is that we had a piece of cardboard that was essentially enclosing the DAGU board to essentially try and simulate a closed environment around it essentially. And if you look here at the side view of the chassis, there's also holes and the wheel, but we removed all of those things. So if you look at the slides here, these are the CAD representation of the robot. If you look, this is the isometric view, the front view, the right view, and the left view. So on the front view, you can see that we've removed holes at the top of the chassis. The reason why we've done this is to simplify the simulation because ANSYS Fluent was struggling to simulate conditions where there was all those holes that are on the real life representation of the chassis. However, we've kept a hose on the front view because those ones, what they do is that they're letting in airflow to the DAGU board, of which is this rad object that is inside this chassis. And if you look at the right view, we've also removed the holes that were there initially for the chassis, for the real life representation of the chassis. The reason why I've done this is also because ANSYS was struggling to simulate with all those holes that were on these views. The back view of the cart is also the same as the front view, so we essentially kept those holes that were already there. Thank you.
To validate the results of the CFD study, we decided to run an experiment in real-life conditions. The DAGU board that we used was mounted on the robot, but we had intended to mount it in a manner similar to the simulation, where we put it inside the chassis of the robot. But because of spatial constraints, we decided it was best to mount the DAGU board on top of the chassis. But then we covered the DAGU board with a cardboard box to simulate what it would be like if the DAGU board was mounted inside the chassis. The room in which the experiment was run was 25 degrees Celsius, and there was no wind in the room. Initially, before any testing was done, the temperature of the chip was measured to be 27.6 degrees Celsius. The robot was allowed to run for 5 minutes and travel around the room, after which the final temperature of the chip was measured, and it was measured to be 34.5 degrees Celsius.
Greetings everyone, I'll be presenting the CFD simulation methodology. The simulation we are looking at is the thermal performance of a chip within a DAGU board when housed inside the robot car chassis. For the simulation, we used ANSYS Fluent from Workbench, the 2021 R2 version. Before diving into the full-scale simulation, we first performed the preliminary test to establish the most suitable mesh size. We opted for a mesh size of 150 micrometers. This size was carefully selected to keep the mesh quality matrix within acceptable standards of a skewness of the mesh being below 0.9, the orthogonal quality above 0.1, and the element quality also above 0.1. This resulted in a mesh-independent convergence. The pictures showed the resultant mesh for the parts of the DAGU board with the chip and 4 spacers and the chassis of the robot car below. The computational settings and physical parameters were as follows. To improve numerical accuracy, double precision was used together with parallel computing using 4 solver processes to speed up the computational process. Gravity was also included to factor in both forced and natural convection. Air was selected as the fluid medium as in real life, but assuming a constant density for computational efficiency. The chip was modeled in the simulation using pure silicon with a thermal conductivity of 150. The DAGU board was modeled as copper, which has a thermal conductivity of 398. The plastic spacers were modeled as plastic ABS. The chip was also modeled as a power source emitting a constant value of 5,142,049 watts per cubic meter. This value was derived from its actual power rating of 0.8 watts, which was scaled by its volume. This then allowed us to simulate the heat generated by the chip. The boundary conditions. The boundary conditions featured an inlet which was set at a constant temperature of 27.6 degrees Celsius, mimicking the ambient temperature of the room where the experiment was done. The inflow speed was set at 0.14 meters per second, which is the speed of the ambient air relative to the straight moving robot car. We then used a laminar flow model selection due to the low speed of the inflowing ambient air. Some simplifications were made for efficiency, one of them being the side walls of the fluid enclosure set to being adiabatic. allowing us to focus our computational resources on the chip where they were most critical. The simulation ran for 40 iterations and achieved convergence around the 25th iteration. We included a buffer to ensure that the solution was thoroughly converged. The picture on the right shows the model with blue arrows showing the inlet airflow and the red arrows showing the outlet airflow from the model.
Good day everyone, my name is Navesh and I'm going to take you through the tail end of this presentation, starting with the results and discussion session. Okay, so once the ANSYS has run through the simulation for us, we can see that we've reached convergence after about 20 iterations, and it's calculated a temperature of 37.564 degrees Celsius. Now this red line over here is the experimental result that my colleague mentioned earlier that was measured to be 34.5 degrees. Now at first glance these two values do not at first glance these two values have a bit of a difference between the two. But is it something that we should worry about? Well, not necessarily. These difference in the values were anticipated, especially for the CFD, because we were aiming for a different approach than with our experimental. So initially, our CFD simulation was considered to be a more conservative approach, mainly due to the assumptions that we made earlier that my colleague spoke about when it came to CAD, as well as the ANSYS fluent settings. And our experimental scenario was a much more lenient approach. My colleague earlier explained about how we used a cardboard box, to try and mimic the DAGU board being in an enclosed space. But obviously, the box could not do a fantastic job because the robot would be moving and that box would move, and it would allow more air to go to cool the board than we would assume, than we would want. So hence, we designed our CFD simulation to be a much more conservative approach, and this was made a much more conservative approach mainly due to the fact that we limited airflow from the sides of the chassis. So there's not going to be any airflow coming from there, and we also used a higher power input than there usually would be, and we did this to try and get a much worse case scenario. So hence a higher value for the temperature in the CFD simulation is expected, and the fact that the difference between the experimental and the CFD is small, it's about 3 degrees Celsius, is a very good and positive thing for us, and we welcome it as a group. Another strong reason that we were expecting a difference is because the chip manufacturer specifies a working range for the chip. Hence, with this, we can sort of use, we can see if the range that we've now calculated, will it actually fit in this working range. Well, in conclusion, we can see that the range that we've got with our experimental and numerical analysis actually does fit within the working range of the chip as specified by the manufacturer, which basically says that the DAGU board is suitable to be mounted within the robot chassis, and with that, it should be able to work perfectly, and there should be no issues with overheating of the board. So now we've concluded that the DAGU board is suitable to be fitted into the chassis, and there should not be any issues with overheating on the chip. But there is much more work that can be done. More detailed numerical analysis can be performed. But before all of this can be performed, there has to be more design decisions made on what will be in the chassis, and the type of chassis that will be used, and how the wires will be managed, because this in effect will be contributing to the things that we'll be using in our new numerical simulation. So yes, while there is much more work that can be done in terms of heat transfer, many design considerations need to be nailed down first before that. Thank you for your time. Have a good day.